Hey everybody! In this video, we are going to learn about the solubility rules for salts, and they are soluble if they can reach a concentration of 0.10 molar, and they are considered insoluble if they cannot reach a concentration of 0.10 molar, and this is all in water, by the way, so it's all aqueous. So, as you might know, all salts can dissolve to a certain degree, but some salts dissolve way better than others, and we classify those that can dissolve very well as soluble, while we classify those that cannot dissolve very well as insoluble. So now let's talk about the rules. So these rules at first might seem really daunting, but if you get some practice in, I'm sure that over time you will be able to figure them out. So these will be the soluble salts, and the exceptions will be listed on the right. So the first rule is that all alkali metal cations and NH4+ are soluble. So any salt with an alkali metal cation like Na+, or maybe Li+, as well as ammonium, are soluble. Now there are no exceptions, so everything with alkali metal cations or NH4+ will be soluble. Now, what about this rule? Most nitrates, acetates, and perchlorates are soluble. The exceptions? None. But note that there may be exceptions out there, but we just don't encounter them that often, so we just consider it to be no exceptions. Now, most chlorides, bromides, and iodides are soluble. Now, the exceptions, well, if it has an Ag+, a Pb2+, a Cu+, or an Hg2, 2+. If these ions are paired up with a chloride, bromide, or iodide, then they will be insoluble. Now, most sulfates are soluble, except for those that are paired up with Ca2+, Sr2+, Ba2+, Ag+, and Pb2+. Now, these three, if you recognize, are from the alkaline earth metals, so that might help you. Now, if you don't know what a nitrate is or a perchlorate is, I recommend you review polyatomic ions in video 2.4, for example, which is on my channel. So now that we have the list of soluble salts gone over, let's go over the insoluble salts. So most metal hydroxides, and metal hydroxide means that it's going to have a metal cation, such as Na+. These are mostly insoluble. The exceptions, well, the alkali metal cations and NH4+ will be exceptions because anything paired up with these two types of cations will always be soluble. And the other ones will be calcium 2+, Sr2+, Ba2+, and Ra2+. So notice that these are just the alkaline earth metals that are at or under calcium on the periodic table. Now, the solubility of alkaline earth metal hydroxides, or anything with a OH that's paired up with any of these four, will increase down the group. So that's cool to know. Now, many carbonates, phosphates, and sulfites are insoluble. The exceptions? Well, we have the alkali metal cations and NH4+. Many sulfites are insoluble as well. And a sulfide is S2-, not to be confused with a sulfite, which is SO3 2-, and a sulfate, which was up here, that's SO4 2-. So, the exceptions for sulfides will be alkali metal cations, alkaline earth metal cations, and NH4+. Now, many chromates are insoluble. The exceptions will be, of course, the alkali metal cations and NH4+, but we also have calcium 2+ and magnesium 2+. So that's something cool. Now, why do certain things dissolve while other things don't? It has to do with a delta H solution, as well as some factors related to entropy. And I discussed that in a solubility video, I think it was 8.2. So go check that out if you want to learn why not all salts dissolve. So now that we went over the rules, let's do some practice, because that's the best way to learn the rules. So we have this compound, sodium acetate, Note that CH3COO- is going to be acetate, and Na plus is going to be the sodium cation. This is going to be soluble because it has Na plus, which is always soluble since it is an alkali metal cation. And also, acetate will always be soluble because that was part of our rules as well, as stated over here, where most acetates are soluble. So this salt will be soluble in water. Now, what about lead 2 chloride? Lead 2 chloride is going to be insoluble because chlorides are usually soluble except for when they are paired with things like Pb2+. So this will be insoluble, and I will shorten that to, how about INS? Now what about these two? We have two compounds of mercury chloride, but one is going to be mercury 2 chloride, and one is going to be mercury 1 chloride. Now there's a difference, because as we saw in the notes, that mercury 1 with a chloride, for example, will be insoluble. So this means that mercury 1 chloride will be insoluble, and since mercury 2 is not on the list of exceptions for chlorides, then this must mean that this one is going to be soluble. And let's do that in green, because green means good and red means bad in this context. Now what about lead 2 sulfide? Now, we know that most sulfides are insoluble except for these exceptions. Is lead 2 there? Nope. So this one is going to be insoluble. What about magnesium sulfide? Well, I think this one's going to be soluble because, as stated in the exceptions, the alkaline earth metal cations combined with the sulfides are going to be soluble. So, therefore, this is going to be soluble. Now, what about ammonium carbonate? So ammonium carbonate will be soluble because anything with ammonium in it is going to be soluble according to the very first rule of our chart. Now, what's our next compound? Lithium chromate. Now this is going to be soluble because lithium is an alkali metal, and all alkali metal cations are soluble regardless of what the anion is. Now what about calcium sulfate? Let's check out the rules. Most sulfates are soluble except for the ones that are paired up with calcium, for example. So this must mean that calcium sulfate is going to be insoluble. Now what about silver iodide, or silver 1 iodide? But you don't really have to say the 1 since silver can only exist as a +1 form. So for silver iodide, this is going to be insoluble because, as we saw in the rules, most iodides are soluble except for the ones paired with Ag+, for example. So AgI will be insoluble. So not that bad, we just used the rules to our advantage to figure out whether these things were soluble or not. Now, let's do some precipitation reactions, and let's write the net ionic equation for these reactions. So all of these are double displacement reactions, so review those if needed. Let's do the double displacement reaction for sodium chloride and calcium hydroxide in solution. So we're going to have to balance things. So I think I'm going to put a 2 here, and I think everything's going to work out from there. So if we mix them up, we will get 2 NaOH, so 2 NaOH plus CaCl2. Now we have to figure out if these are aqueous or solid, because the ones that are solids are the insoluble ones. So we know that sodium hydroxide is going to be soluble since sodium is an ion that will always be soluble. Now what about calcium chloride? Is calcium chloride going to be soluble? Let's look at our rules. So it says most chlorides are soluble except for these ones. Is calcium on that list? No. So this must mean that calcium chloride is going to also be soluble. Now how do we write the net ionic equation? Well, I like to split up the things if they are aqueous, of course. So 2Na plus aqueous plus 2Cl minus aqueous. And I'm doing this with a messy writing because I'm going fast. And calcium 2 plus aqueous and 2OH minus aqueous will give us 2Na plus aqueous plus 2OH minus aqueous plus 1 calcium 2 plus aqueous plus 2Cl minus aqueous. And what cancels out in this? Well, we see that the sodiums are spectator ions, our chlorides are spectator ions, our hydroxides are spectator ions, and our calciums are spectator ions. So we can conclude that there is no net ionic equation, and therefore you can write no reaction, because what is essentially happening is that you are mixing two salts, and since nothing is solidifying, that means that nothing is happening, and all they're doing is going to solution, which is a physical change. So no reaction here, because there's no chemical changes going on. Now what about this? Lead 2 perchlorate plus NH4Cl will give us what? Well, let's do some mixing up, and we get, well, we have to balance things first, so I think I will put a 2 here, and that should work things out. So lead 2 chloride plus 2 NH4Cl4, so ammonium perchlorate. What a large chemical formula, honestly. So will this PbCl2 be solid, or will it be aqueous? Or in other words, will it be soluble or insoluble? Well, I think this is going to be insoluble, so it's going to be a solid, since chlorides will precipitate with lead 2+. Now what about NH4Cl4? Now this one is aqueous because NH4+ is always soluble. So now we can do some net ionic equations. So we have to split up our aqueous salts into ions, since that's how they naturally exist in solution, since they are separated most of the time. So Pb2 plus aqueous plus 2ClO4 aqueous plus 2NH4 plus aqueous plus 2Cl minus aqueous will give us, let's see, PbCl2 solid, since we don't separate solids since they're together, and 2NH4 plus 2ClO4 minus, and these two are aqueous, and I forgot to put that. So which ones are spectator ions? Well, I think our perchlorates will be, and our ammoniums will be, and in the end, our net ionic equation will be Pb2 plus aqueous plus 2Cl minus aqueous to give us 1 lead 2 chloride solid. Now this is going to be our net ionic equation. And yeah, let's do one more question. MgS plus BaOH. So we are going to do the switcheroo again, and we have to balance things first. So let's see. Oh, I think I messed up something. So this OH is supposed to be OH2, since hydroxide is -1 and Ba is +2. So my mistake there. Sorry for that. And let's see. How do we balance this? Well, I don't think we have to balance anything. So let's just move forward. So we do the switcheroo and we get MgOH2 plus BAS. So which ones are solids and which ones are aqueous? Well, let's check out this magnesium hydroxide first. So magnesium hydroxide will actually be insoluble, since it's not part of the exceptions. Since Mg2 plus is not on this list, then the MgOH2 will be insoluble. So we will write this as insoluble, so it will be a solid. Now what about barium sulfide? Well, we know that most sulfides are insoluble, but since barium 2 plus is in the alkaline earth metal cation group, then that means that our BAS will actually be soluble and be able to dissolve into the aqueous solution. So now we can write our net ionic equation. Now let me show you a cool shortcut that I do. So for the solid, keep it, and let's put a protective barrier around the ones that we want to keep. And let's remove the ones we don't like. So these aqueous ones, Ba and S, are not wanted. And we're left with Mg aqueous. Well, we have to put the charge Mg2 plus 2OH minus aqueous will give us MgOH2 and this will be solid since it precipitates. And this will be our net ionic equation for this reaction. So that's all for this video. I hope you learned a lot, and have a wonderful day, everybody.